All right, so now we're going to look at something we call the internal energy of a gas, which is not really a new form of energy. It's just a way we describe it. But the average kinetic energy we talked about from the kinetic theory of gas is the average kinetic energy from a single molecule of gas is given by this formula. Now, its kinetic average is 1/2 v RMS squared. Let's talk about this v RMS squared. It's not average speed or average velocity. It's more like you're going to sum up the velocity squared of every molecule and then divide it by the total number. Okay, and this gives you the RMS, and then you take the square root of this, and then this gives you the RMS. This is like the average square of the velocity, root mean square. Doesn't really matter. The derivation of it is like kind of beyond the scope of this class, but that's what VRMS means. So that's the average kinetic energy from one molecule of gas. So it's average, right? It's also given by this formula, 3/2 kb times T. And this is just directly relating that the average kinetic energy is related to the temperature of the gas. So what are the average kinetic energy of the gas? It doesn't matter how many molecules there are. It's 3/2 times this constant times the temperature. It's directly related. The temperature is proportional to how much kinetic energy is. Now, if you were to take a gas and add up all the kinetic energy, you were to take every single molecule of gas in a container and add up the kinetic energy of all of them, then you would have the total kinetic energy of all the atoms in the gas. And that's what we call the internal energy. So U is what we use for energy. It was often used before for potential energy, but it basically means the same thing. It's an energy. It's the number of molecules times the average. So it would be N times this. So it'd be 3/2 N times kb times T. But remember that N kb times T was NR. Like this was also NR in terms of moles. So 3/2 NRT. So this gives you a formula, and it's very similar to PV equals nRT, right? Very similar to ideal gas law. But the internal energy, a couple things I want you to note, is that it depends on the number of molecules and then just the temperature. And that is a proxy for the total kinetic energy. Now, physically, the internal energy is nothing more than the total kinetic energy of the gas. That is at its core what we mean by the internal energy of the gas, okay? Now, that might translate into a higher temperature, okay? So remember that kinetic energy, if it's greater, then it's got to have a higher temperature. And so one of the things we talk about is how does the internal energy change? How do we increase or decrease the kinetic energy? And it happens by collisions ultimately at its fundamental. If you were to zoom in a little bit about it's like when you have hot gas reacting with cold gas, they're colliding with each other, transferring kinetic energy until the average kinetic energy is kind of like a little bit more uniform. We call that kind of transition, that transferring of energy from one temperature or one set of gas that might have higher kinetic energy versus another gas that might have lower kinetic energy. We call that heat flow. Okay, when a hot gas, so like when you're talking about, like we talk about heat, like an oven, you heat up the oven. How is the oven getting heated up? Why is the air getting hotter? It has to do with the fact that you have heating coils. They get hot through magic right now. We'll learn about it later, but it generates heat. And that then the air molecules hit that metal that's hot and then come out of it with more kinetic energy. And so then the air then increases, and that is heat flow. That's what we're talking about here. Now, Q is used to denote the heat or energy. Q is measured in joules. It is a form of energy when we're talking about heat flow, because again, it's the transferring of kinetic energy. So in an elastic collision, the total energy remains constant, but the faster molecule may slow down, loses some kinetic energy, and the slower molecule may speed up to gain kinetic energy. So the hotter molecule might cool down, and the cooler object might heat up. That's exactly how that transfer and heat. And that's at its core, that's what heat is, right? It's this transferring of energy. Now, in order to change the internal energy, if you think about just more macroscopically, so we have energy, gas contains energy. It's made up of the kinetic energy of the gas molecules, but it has energy. There's two ways you can change the energy of the gas. You can either do work on the gas, right? Remember, work is the change in energy. So you can do positive work on the gas that will give it energy, or you can add heat as added to the gas. So we ultimately look at the change in energy by this equation. You can either, if I want to increase the energy, I can either add heat to it or I can do work on it. Right? And so that's pretty much all it is. And remember, Q is just like this proxy of, the transferring of kinetic energy from these collisions. But we try to abstract away and just say, like, look, you have a hotter thing, you have a cooler thing. The hot thing can warm up the cooler thing. and it can gain temperature and gain energy, right? Gain internal energy. So that's why this formula comes about. And this is all I think about is like, oh, the change in internal energy is how much heat is added to the gas plus how much work you do on the gas. And some of those might be zero in some situations. The internal energy of the gas will decrease when negative work is done on the gas. So let's talk about the work, the sign of work being positive or negative. So remember, work was the force displacement, and we said positive work was when the force and the displacement were in the same direction, and negative work was when the force and the displacement were negative directions or opposite directions. Right? That was the idea. And so when you have a container of gas, let's say I have a container of gas and it's full of gas molecules in here. And how would and these gas molecules, because they're bouncing off the walls here, they're going to hit it and they apply pressure. There's some force here. If I were to do positive work on the gas, it would be like squeezing the container. I would push a force in this direction and the displacement would be this direction. So that's positive work on the gas. Is I'm squeezing it and it's getting smaller, right? Like my force and my displacement are opposite directions or the same direction. So compressing a gas is positive work. All right, that's the main idea up there. Now, if the gas expands, let's say the displacement were the opposite direction. So now the displacement's going the other direction. I'm still squeezing it. It's like I'm trying to push it, right? Because the gas is like trying to escape, right? So I'm holding it in place. But if it expands, now we're doing negative work is being done on the gas. So expanding gas is negative work. The work would be less than zero. Okay, so negative work's on the gas. And if you do negative work on the gas, then obviously that means that we lost energy, right? Because then this part would be negative. So internal energy gas will decrease when negative work is done on the gas or heat is removed from the gas. Now, there's this expression about the work is pressure times volume, assuming that the pressure is constant. Okay, if you think about the work as being force times the displacement, but in terms of the area, right, force is the pressure divided by the area times the displacement. So let's say I'm compressing the gas again, right? So I'm compressing it. And so the container goes from there to, say, there. So it shrinks, right? We're compressing the gas. And this distance here is the displacement. Okay, if I do the displacement, sorry, I have this wrong. Force is pressure times area. Pressure times area. Because remember, force divided by area is equal to pressure. So the area of this circle times how much I squeezed it is that change in volume. So we call that pressure times the change in volume. Now, in this case, if I compress it, then the volume, then this will be negative, but compressing is supposed to be positive work, so we put a minus sign to make it positive. Okay? So that's where that formula comes from. All right, that's how it's derived. So couple of tips. Work done by the gas is equal to the work done on the gas, but opposite done. So you'll see, like I said, the way I defined this W when we use this formula, this is work done on the gas, but sometimes you're asked by the gas. By the gas is opposite, because by the gas is doing a force opposite the direction. Newton's third law of motion, right? So the gas is pushing outwards, I'm pushing inwards, right? Equal and opposite forces. I push on the gas pushes on me. Q is either given directly in the problem, like the heat, or must be solved indirectly by finding it. So we're going to pair this very often with the ideal gas law. So when we take a look at this, so let's look at a few examples of problems here. So we have 0.5 mole of gas at pressure this expands from a volume of 3 to 5 cubic meters. Assume that the pressure of the gas stays the same the entire time. How much work does the system do on the gas? Okay, so external force. So that work is, again, that negative P delta V. And because it's expanding and I'm pushing this way, I'm trying to like prevent it from expanding, right? So my external force would be inward because the gas is pushing outward. And so that's negative work, right? So it's negative times the pressure, 2 times 10 to the 5th. And then the change in volume, final volume minus the initial volume is going to be that. So that's going to be negative 4 times 10 to the 5th joules. This would be 2 times 2. Did the internal energy increase or decrease? Okay, this is a great question. So let's calculate that change in the internal energy. We don't know about the Q, so you don't want to use here. You might think like, oh, I should use the Q plus W. But I don't know if heat was added or removed. All I know is that it expanded, so I don't know about this value. So this is not going to help me here. But I also know that the internal energy is related to the 3/2 nRT, right? That's that relates the internal energy. So then the question is oh, another way to think about it is for internal energy is, did the temperature increase or decrease? And that's where we might use PV equals nRT, use ideal gas law. Okay, so then we say like, oh, okay, so here the pressure was constant, the volume went up, nR remained the same, the temperature went up. So that means it has to increase. See? Because the temperature went up. Temperature went up, and it's because the temperature went up. Temperature increased when pressure was constant and the volume increased, right? So it's the temperature increased. Okay, so how do we calculate that change in internal energy? Well, you just do U final minus U initial, and that would be 3/2 nRT, the final temperature, minus 3/2 nR times the initial temperature. Now, in this case, the NR, we know PV equals nRT, because I don't actually know the temperature, but you could calculate the temperatures by just saying like, well, I don't know NR, but I know the temperature is going to be PV equals N over NR, right? And so then you could say like, oh, well, the final temperature is going to be 3/2 nR times the final state of the pressure, right? So the pressure was going to be 2 times 10 to the 5th times the final volume, 5 over nR. I don't know what nR is, but it's going to cancel with that there. Minus 3/2 nR times the initial temperature, which would have been 2 times 10 to the 5th times 3 cubic meters, the PV over nR. But here the nR's cancel. So then you could just calculate the internal energy directly, just because I know the pressure and the volume. And so then I can look at the change in temperature. 5 times 2, and that gives me 600, or a 6 times 10 to the 1, 2, 3, 4, 5, 5th joules. Okay, was heat added or removed from the system? Well, now we can look at this. We know the internal energy was, it gained energy, 6.5 times 10 to the 5th. It's Q, and then the work was negative. So the Q is going to be positive. It's going to be 10 times 10 to the 5th joules, right? You add that over. And so heat was added because Q was greater than 0. Okay, so if Q is less than 0, then heat was removed from the system. Okay, it takes 500 joules of work to compress 0.5 mole of an ideal gas to 1/5 of its original volume. Assume there was no change in the temperature of the gas. Was work done on the gas or by the gas? So let's think about the gas here. We're gas and we're going to 1/5 of its original volume. So we're shrinking it, right? And we're going to do a force to shrink that. So that's going to be done on the gas. So we say positive work was done on the gas. If the initial pressure was P0, find the pressure after the gas was compressed. Okay, so here, there was no change in temperature of the gas, so they kept that gas. So we're going to use a PV equals nRT. Okay, and so here, we're going to say like, oh, well, we know that initially, P0 times the initial volume is equal to nR times the initial temperature. And then the final pressure is same volume, 1/5 of the original volume. So it's going to be 1/5 of the original volume. nR is the same. And then the final temperature is the same, still the same temperature here. Okay, so what ended up happening, if you look at this expression, is we kept the temperature constant, right? And the volume got multiplied by 1/5. These are all constant, so in order to keep it balanced, this has to get multiplied by 5. So we would say it's 5 P0. Now, is heat added to or removed from the gas? Well, think about it 2 ways, right? Change in internal energy is Q plus W. And the internal energy didn't change because the temperature didn't change. So this was 0 because there's no change in temperature. Because remember, the temperature relates how much kinetic energy there is, how much internal energy is. So the change, it's not that there's no energy, it's just that there's no change in temperature. Now the work was positive work, right? We said we did positive work here. So if the total is 0, then this number has to be negative. And if it's negative, that means heat was removed. So Q is less than 0. So that means heat was removed from the gas. Okay. Let's look at another example. When 2 moles of gas changes from a volume of 10 to 2 cubic meters at constant pressure, 1,500 joules of work is done on the gas. What is the pressure of the gas? So we have PV equals nRT, right? Constant pressure. So this is one of those where it's like, okay, let's see what we know. We know that we know that this is 2. We know this is 8.3145. We don't know the temperature, but we know the volume, the constant pressure. We will know that this the volume decreased, right? And so it went from 10 to 2. So yeah, we know what those values are, but I don't know the temperature. I don't know the pressure. So what else do we know? So this is not enough, right? Like I don't know the temperature. I want to find the pressure. Well, I don't know the temperature, so there's not enough information to solve for the pressure there. But we know the work, because the constant pressure is negative P delta V, right? Because I compressed it, and I know the work part, so we want to use that information, right? So the work, negative work divided by the change in volume is going to be the pressure. So that's going to be negative 1,500. And what's the change in volume? Is you ended at 2 and you start at 10. And so we're going to be left with 1,500 divided by 8, and that's going to be 187.5 pascals. Very low pressure here. Okay, what's the change in temperature of the gas? Well, now we want to look at the PV equals nRT. Because we know the pressure is the same, we want to look at the final temperature minus the initial temperature. And that would be, if you look at this, T is equal to PV over nR. Right, so we're going to look at the final pressure. The pressure stays the same. We're just going to look at the final volume over nR minus the pressure, the initial over nR. And we know the moles of gas, so this is 187.5 divided. Let's factor out the P over nR. So it's going to be P over nR times the final volume minus the initial volume. Just factor that out. nR is going to be 2. 2 is the number of moles in the gas. 8.3145. And then the change in volume would be T minus 10, 2 minus 10. Because it ended at 2 and it started at 10. So the temperature decreased. That's going to be negative 90 degrees Kelvin, or 90 Kelvin there. Okay, so that is what I got there. What is the change in internal energy of the gas? Okay, so change in internal energy of the gas. Again, we don't know the Q, so we can't use that, but we can use 3/2 nRT for their part there. So you could look at the change in energy because N and R are constant, and we know that N and R is going to be 3/2 or nR times the change in the temperature here, right? Because it's going to be final minus the initial, and you can factor out because these are all constant, right? So this is going to be 3/2 times 2. Sorry, this shouldn't have made that so ugly. nR times the change in temperature. So that's going to be 3/2 times 2 times 8.3145. And the change in temperature is minus 90 degrees, right? So it's just going to be that number times 8.3145 times 3, and that's going to be negative 2250 joules. And we want to know if heat was added or removed from the gas. So this is where we can look at this equation now, right? Because now we can talk about whether Q is positive. We know the change in internal energy was negative 2250. We know the work was positive 1,500 joules. Right, and so then the Q is then going to be, you subtract that, it's going to be negative 3750 joules. And so then we removed heat because the Q is less than 0. Okay, just like that. Thanks for checking out this video. I hope you found it really helpful. If you'd like more support, maybe you need more multiple choice practice, maybe you just need more guidance and things like that, I have plenty of information on my website. If you look in the description below and go to www.bothellstemcoach.com, I will explain all the ways I help students be successful in their AP classes.